All right. I think we should start because it's already 10:04. So first of all, welcome to all of you. Can I, because this is the first time we are meeting, can you please, anyone of you, please let me know. All of you are postgraduate students, master students there, right? Uh,
Yes.
Okay, and you are present there physically, or all the classes are online at the moment?
Online, probably.
Okay. Also, I would just so I have been told by the university that you have background in quantum mechanics, quantum electrodynamics, and solid state devices. Is that so? Is all of you have some background in quantum mechanics, quantum electrodynamics, right? Can I assume that, or should I uh, discuss without any assumption, without any background uh, into consideration?
Well, we have a course recently, so maybe
Okay.
just a little reminder probably would be sufficient.
Okay. So maybe what I'll do is I will go through the content right from the basics, and if you find the content to be slow paced, to be slow, you please let me know. I'll maybe go faster. And at any point, if you feel that I am going slow or I'm going fast, please let me know. If you are not able to get anything, please stop me. And if you have any question at any point of time, in that case also, please interrupt. Right? So please consider this to be like a discussion. Although I know that online classes are not so engaging, not so effective, because here at IIT Roorkee, we also had online classes for 2 years, and the experience has not been so great, right? So, considering the limitations of online classes, let's try to make it as effective as possible. Okay, and for that, if you can have discussions in the classes, that will be very good. Okay. Uh, can you see the slides on your screens? Do you see the slides on the screens? Anyone, please confirm this, and then maybe I'll start.
Yes, we can see it.
Okay. So as I told, if at any point if you find things, if you have any question or anything needs to be discussed, please let me know. Also, did you had a chance to go through the video that I recorded last week? That was a very basic video, very uh, elementary kind. Anybody has seen that or not? If not, that's also fine. Actually, that's not a problem because it's the beginning of the semester, so things take time to start, I think. Right? Okay, so
Excuse me, but I don't see the slides.
I do.
uh, you cannot see the slides, right? But some of
Right.
you can see the slides. Some of you can see the slides, I hope, right? Okay, let me do this. I'll unshare and then share it again.
Now I see the. Yes, now I
Okay.
see the slides.
Okay, now you can see. Okay, great.
Thank you.
So yes, okay. So let's begin this discussion, and I will assume that you may not have gone through the video that I posted last week. There was some confusion about the timing and the themes of the classes. So this course is about the fundamentals of nanoelectronic devices, and I am Vishwendra Singh Punia from IIT Roorkee, and today I will quickly take you through through the background that I gave last week, and then we will discuss about the basics that we would need in this course, right? And as I said, please interrupt me if you have any question at any point of time. Okay, so what I told last week is that essentially the electronics is the story of the conquest of electron. Conquest means that that in electronics, everything boils down to controlling the flow of electrons in a piece of semiconductor, right? So ultimately, that's what we do in electron. In all electronic devices, we want a controlled and desired flow of electrons. So for that, we need to understand the nature of electrons, because that's what we are trying to control. And in the previous class, what I discussed was I discussed this thought experiment, which was originally proposed by Feynman, and it explains the nature of electrons very beautifully, because in this experiment we have a Young's double slit like setup in which we have two slits. There is a, and after the slits there is a this screen on which we can see the particles coming through the slits. So if we do this experiment with classical particles, then we observe this kind of pattern. Okay. So I explained this thing in detail in the previous class. I request all of you to go back to that video that is uploaded on the recordings section of the Teams page, because it will take too much time if I explain things in the same detail today itself. So, but I'll briefly summarize this. In the Young's double slit experiment, if we do the experiment with classical particles, the final output that we will obtain is like this, when both the slits are open. If we do the same experiment with waves, the water wave or the sound wave or any kind of classical waves, we will get the interference pattern on the screen like this, right? And that is the distinctive feature, that is the differentiating feature between the particles and the waves. Now, let's do the same experiment with electrons. We have a source of electrons, an electron gun. We have a double slit on a wall. And after the wall, we have a backstop where there is a detector which detects the electrons. So I hope all of us would agree that, so this is the pattern. If only slit 1 is open, the pattern or the probability of receiving electron as a function of x is P1. And if only slit 2 is open, the probability is P2 in this plot. But if both the slits are open simultaneously, in that case, we observe the pattern which is quite similar to the waves. And that's why we claim that electrons behave like waves. But this is not as simple as that, because if we slightly modify this setup and if we put a light source right after the slits here, a light source here, and what does this light source do? This light source essentially interacts with the electrons coming out of the slits, and electrons will scatter the light, and that way we will observe the electrons, or we will make a measurement of the state of the electron, right? In that case, the probability distribution of detecting electron at the screen when only slit 1 is open is still P1, which is written as P1 prime here. The probability distribution when only slit 2 is open is P2, but when both the slits are open simultaneously, the distribution changes to this way. The distribution will change to the distribution of a essentially like a classical particle. So the same particle, same electrons, when we are not observing them, they are behaving or they are exhibiting a wave-like nature. And when we make a measurement, they exhibit a particle-like nature, right? So that is the interesting property about electron, and I hope that all of you would be familiar with that, because this is just a basic stuff about electrons. Because once we make a measurement on the state of the electron, the state collapses to one of the eigenstates of the measurement operator. So we'll come to that later. But what the takeaway here is that electrons are quite a complex particles. They are not simple like elect uh, simple like classical particles and classical waves. So that's why we need to use a different kind of treatment to understand the behavior of electrons. Okay. And before going into that, let me briefly discuss about the history of electronics. So the history, because I also discussed this in the last class, that generally when we start a subject, I always try to give a big picture of that subject, because that way we can connect what we are studying to the historical developments as well. So let me quickly go through this. The history of electronics is roughly divided in three parts. One is the pre-20th century time, before 20th century, and in that time, almost no electronics existed in the common man's life. So it was the time when electricity was being studied, the magnetism was being studied, and electromagnetism was studied rigorously. And some electrical devices were there. Electrical devices means the electric transmission lines, motors, AC motors, DC motors, and appliances based on those things. The birth of electronics actually is considered to be started with the invention of the vacuum tube diode. So vacuum tube diodes were invented at the beginning of 20th century, and that is the time when the electronics actually as a discipline started. And soon after the vacuum tube triode was also invented, and that's the time when electronics actually started. Uh, and this went on for around 40 years and up to 1947. And in that time, many electronic components were, many electronic appliances, many electronic systems were built on the diode and the triode. For example, even a computer was built based on triodes in 1930s or 40s, that which was also used during World War II. But uh, the real breakthrough came in 1947, December 1947, when the first point contact transistor was demonstrated in Bell Labs. And so that is the birth of the solid state electronics. So this time, the 1947 is the time of birth of solid state electronics, and that is also uh, some people call it the transistor era. Okay, and these are three major milestones in the development of electronics as a discipline. So these are some pre-electronics era developments. These are some of the prominent names in that. And in that time, electromagnetism, I discussed this in detail in the previous class, so please go back to that. And if you have any questions, then we can discuss that in the next class. So one of the most important contributions in pre-electronics era was by Maxwell, because Maxwell was the one who gave a unified theory of electric and magnetic fields, also uh, the unified theory of light, electricity, and magnetism, the so-called electromagnetic equations of Maxwell. And that was considered to be one of the greatest development of that time. And some people believed that that is the end of physics in a sense, because they thought that they have understood everything. Because once the light waves, the electricity, the magnetism, and everything could be explained using Maxwell's equation, then people thought that it is all. But then soon after that, quantum mechanics came up and everything changed. Okay, so that was pre-electronics era. Then in early 20th century, 1904, vacuum tube diode was invented by Fleming. And in this, so you might be aware that the vacuum tube diode has is quite similar to a bulb, a light bulb, which was invented by Edison. And in fact, Fleming used to work in Edison's lab, and that's where he got this idea of uh, uh, making a vacuum tube diode. So the interesting feature was that in a diode, we have a source of electrons. So one electrode was heated and it was emitting electrons, and another electrode called anode. If we apply positive voltage here on the anode, it will attract electrons, and that way the current will flow through the device. But if we apply a negative voltage, it will repel the electrons and no current will be there. So that way, depending on the applied voltage on the anode, we could either allow the flow of current or we could block the flow of current in the system. So that is uh, uh, that is essentially a primitive PN junction, because PN junction also essentially does the same thing. But this was based on vacuum tube, and many uh, inventions were done based on this, because this worked as a rectifier, so which could convert AC light to DC light. And soon after vacuum tube diode, a third terminal was inserted in the a third terminal was inserted between the 2 points. So yeah, and that's how the vacuum tube triode came up. So triode has an interesting functionality, that there was this third terminal in the triode, which was between the cathode and the anode. And on this third terminal, even if we applied a small signal, we will get a large signal across the anode. So that's how this concept of amplification came into picture, because it acted like amplifier. We could amplify a small signal which was applied at the third terminal, because this terminal was closer to the cathode. So even a small signal that was applied on this could result in large variations in the current in the system. Okay, so this was about the early vacuum tube diode and triode history. And as I told, there were many technologies that were built upon this. For example, the radio communication technology, the television technology, and even a computer was built upon, radar computer was built based on this. Then came uh, uh, actually the quantum mechanics. Quantum mechanics is considered to be the milestone in development of electronics, because through quantum mechanics, we could understand the nature of electrons in a better way, which means that the theory, so once the initial development of quantum mechanics happened in 1920s, then in 1930s, we could understand the theory of solids, the properties of solids in more detail. Okay. And once the understanding of conductivity of solids from quantum mechanical lenses happened, then people started thinking about using those concepts in making solid state devices, because there were many problems with vacuum tube electronics, because the tubes were not so efficient. They were high maintenance. They could be easily broken. And uh, so, for example, if we have a device, if we have a computer in which there are 1,000 tubes, and if one tube goes bad, it was extremely difficult to detect that and replace that. Okay, so the development of solid state electronics became possible only after uh, uh, the quantum mechanical theory of solids came up. And then finally in 1947, the point contact transistor was demonstrated in the Bell Lab. So I discussed this in the previous class as well. And although the idea of FET, which is field effect transistor, is quite old, the idea was given in 1926. But because of the interface between the two solids, there are many defects at the interface. Because of that, the fabrication could not be done for a long time. And that's why first in 1947, BJT point contact transistor was demonstrated, and in 1948, BJT was demonstrated. But it was also not possible to make large scale systems using just transistors. And the real push to the technology to electronics came in 1960s, when the integrated circuits could be made with the transistors. So what do we mean by integrated circuits? Anybody here, can you please uh, tell what is an IC? Uh, Anyone, whatever you know, that's it's not a
Integrated circuit is a circuit that um, is integrated in one chip. The components of the circuit are on one chip.
exactly. So yeah, that's how we define integrated circuit. So essentially, if we put a large number of transistors on a single piece of semiconductor, that is called integration. Okay, so integration means putting a lot of transistors, lot of circuit elements on a single piece of semiconductor, on a single chip, as she pointed out. And that only became possible in 1960s, and that is also the time when Intel was founded. Okay, and that is essentially the time when this technology, the electronics as a discipline, actually blew up. So this is a plot which you might have seen at many places also. So on the x-axis we have the years 1970s to 2010. And there are two y-axis. On this axis we have the cost per transistor. On this y-axis we have the transistors per chip, which means number of transistors on let's say 1 centimeter by 1 centimeter piece of silicon. So on this single piece of silicon, this y-axis shows uh, the second y-axis shows the number of transistors. So as you can see that right from 1970s, when the number of transistors on a single chip was around few hundreds or 1,000, at the moment, or in 2010, the number of transistors were approaching a billion, 10 to the power 9. So this kind of growth is was not seen anywhere else, or generally in any other technology. When just in a period of 40 years, the number of transistors on a single piece of silicon, on 1 centimeter square of silicon, increased from 1,000 to around 1 billion. Right, uh, and there is an empirical or a trend defined by Moore's law. Essentially, Moore's law is says that, or it was a trend. It is not a fundamental law. It says that the number of transistors on a single uh, chip, on a single IC, would increase or would double every 18 to 24 months. So roughly every 2 years, the number of transistors or the density of the chip would be double. And this was the trend which was given by the co-founder of Intel, looking at the trends of 1970s. And this, interestingly, this Moore's law is being obeyed almost till 2014 or 2020. Now people are talking that the Moore's law has saturated, and uh, now it is no longer possible to increase the number of transistors. Although that is still going on, but there is some it is hitting a saturation. Okay, so that was the background of this discipline. And in this slide, I have the evolution of the semiconductor technology. And in this, uh, by the semiconductor technology, I will primarily be talking about the transistor. Moreover, it is the MOSFET, which is metal oxide semiconductor field effect transistor. I hope all of you are aware of this device. All of you know about the basics of the MOSFET or not. You might have heard or learned about it in one of your previous courses or your undergrad.
Yes, we know about that.
Yeah. So a MOSFET, as all of us, I hope, know, that is a device in which we have a piece of semiconductor, let's say this blue region, on which we have two contacts, the source and the drain contacts. And in between the two contacts, so these are a different, so if this is a P silicon, the contacts are N-type silicon. And in between the two contacts, we have what is known as the channel region. So this region is the channel region, which is the most important region of the MOSFET. And on top of the channel region, we have oxide, the insulator. And on top of that, we have the third terminal, the gate terminal, right? Or in summary, what we can say is, to simplify things, that this is the most important part of the MOSFET, which is the region between the source and the drain, right? And this is called the channel region. Okay, and then we will have an insulator and we will have a gate as well. But we are not too much concerned about the gate at the moment. We will be mostly focused on the channel at first, because if we understand the properties of the channel first, then things are simpler. The life becomes simpler. The evolution of semiconductor technology has happened as I just told, according to the Moore's law, and that is called the scaling of the transistor. By scaling, I mean the size of the transistor, the size of the channel particularly, has been continuously going down and down, which means the size of the entire transistor is decreasing, and that is making it possible to put more transistors on the same chip, on the same piece of semiconductor. But what is happening to this channel during the scaling, during the evolution of semiconductor technology? This L is the channel length, roughly defined as the distance between the source and the drain. So this is these are the typical figures, or this is the channel length L, and this is the years. So in 1971, 1970s, the channel length was around few micrometers, tens of micrometers. It was the time when ICs were first built, and the channel length was around 10 micrometers. Then in around 12 years, 1984, the channel length was 1 micrometer. And after 30 years, in 2016, the channel length, or at the advent of 21st century, the channel length was in few micrometers, actually 20 micrometers, 40 micrometers. And 2016 was the year when the 10 nanometer technology was launched. 10 nanometer node actually came into fashion. So now this is interesting. This figure, 10 nanometer or few nanometer, is interesting because that is where the nanoelectronics come into being. We had a conventional theory of conductivity in these devices in 1970s, 80s, which essentially came from the Roots model. Roots model. I hope you are familiar with the Roots model of conductivity, which is used in conventional semiconductor physics devices. So most of the times in our undergrads, we study the Roots model, the conductivity defined using that. But the problem is that in 2014 or 2010, when the channel was shrinking and the channel length was only 20 nanometer or so, it was becoming difficult to reduce the length of the channel. Because making such a small channel precisely and having a very good surface was extremely difficult. So that's why in 2016-17 this length actually saturated. So even now in 2022, the semiconductor industry is operating at 5 nanometer, 3 nanometer technology nodes. But in these technology nodes, the length of the channel or the distance between the two contacts, it is not 5 nanometer or 3 nanometer. These are just names of the technology nodes. The actual distance is something different. It is still in tens of nanometer, 10 nanometer, or between 10 and 20 nanometer or so. But using other methods, using indirect methods, for example, by putting gate around multiple sides of the channel, still the density of the chip is being increased, and that's why uh, companies are calling that they are reducing the technology node, because they are increasing the density of the chip and they are increasing the performance. But this does not correspond to the actual channel. So that is, in current time, the channel length and the technology node, they do not have anything in common. So that these two are different numbers. So what essentially it means is that at the moment, in current transistors, we are still operating in a device, we are still have a transistor in which the electrons will travel from source to drain, and in between channel we have only, let's say, 10 to 20 nanometer distance. Now the question is, uh, and this is the distance between, this is the channel length nowadays, and uh, the atomic dimension is few angstroms, right? So which means that we only have, let's say, around few tens to few hundreds of atoms in the channel at the moment. But the question that we will ask in this course is, what is, what changes when we go from, let's say, 1 micrometer channel to 10 nanometer channel? What changes in the electrical properties of the electrons? What changes with the device, or how does the physics change? Anybody, can anybody comment here? What would change if we reduce the channel length continuously?
When we go to that small scale, we have effects that appear only on that small scale, like electron channeling, channel effect. So this is the problem when we um, this is a problem of going to that small scale, because these nano effects appear in device.
Okay, okay, yeah, that's a valid point. Anybody else? Okay, so so as she mentioned, one of the things that appears is that effects like quantum tunneling uh, uh, start becoming prominent. But I would add to this point that quantum tunneling is prominent when the distance of the barrier thickness is, let's say, 3 to 8 nanometer or so. So the tunneling is prominent in this dimension mostly when uh, the distance, or when the channel length is less than, or it is around 1 to 2 nanometer. At this point, still the actual distance between the source and the drain is let's say 10 to 20 nanometer. So tunneling is not so big a problem at the moment. The first thing that uh, changes is that the way electron. So ultimately, what happens is that when we apply a battery on this device, which means the source is connected to the ground and the drain is connected to a voltage V. So that's how we establish a current in the circuit. So in this case, what happens is that electron will start from the source and it will go to the drain via channel. Okay. Very simply, the MOSFET current is when electron starts from the source, travels through the channel, goes to the drain, and then taken by the battery, again supplied to the other terminal. So that's how the current actually travels in the MOSFET. Right. At these dimensions, when the channel length was let's say a few tens of micrometer, at these dimensions, the way electrons travel is this. So this is the source, this is the drain, and this is just the channel region. So electron will start from the source. It will enter into the drain. It will collide with maybe to the lattice atom or to the other electrons or anything, and it will have a zigzag path. So it will undergo multiple collisions in the channel, and finally what will happen is some of these electrons will reach to the drain, and some of these electrons will lose the energy in the channel itself. So they may not go to the drain side. And with this assumption, the classical uh, semiconductor theory is built upon. So generally, the way we visualize the electron motion in channel is that electrons start from one of the contacts, they undergo multiple collisions, and then they go to the drain. Okay, but the problem is that in modern day devices, electrons, so the channel length is so small, 10 to 20 nanometers, that electrons will start from the source and they will directly go to the drain without any collision in the channel, without any scattering in the channel, right? And that's fundamentally different from this kind of transport. So this transport in which electrons have multiple scattering in the channel is called as the diffusive transport. Diffusive means electrons starting from one side, they are undergoing multiple scattering. So they are in a way diffusing like gas particles from one high concentration to lower concentration. But nowadays, this is not happening. This is electrons are starting from the source, directly going to the drain, and this is called as the ballistic transport. Ballistic, in a way, means it is like bullet. It is going straight from the source to the drain. And our classical understanding of electronics is built on this kind of picture. For example, if I ask you, uh, how does the resistance come into picture? Or what is the source of resistance in a conductor? What is your answer to that? What would be your answer to that? Why does a conductor has resistance? Or why does any electronic device has resistance?
Maybe
Anybody?
because of lattice, crystal lattice.
Yes, exactly. So the conventional understanding is uh, that electrons collide with the lattice atoms, right? And because of the scattering to the lattice atom, the resistance comes into picture, right? So you are right. So the source of resistance is generally in our classical understanding, the source of resistance comes from the collisions in with the lattice atoms, right? Now my question to you is, if the electrons are not colliding in the channel, let's say this case, which is actually happening in modern day devices, which is happening in our cell phones and our computers right now. Electrons are having ballistic transport. Would still be would there be resistance in these devices, or they will not have any resistance? Or what is your what do you think? Does resistance still exist in devices?
Well, I think it's really impossible that there is no resistance at all. So I think there will be some resistance, but it's hard to understand why then it appears if no collisions.
Yes, exactly. So yeah, so we have a feeling, we have an intuition that resistance cannot go away because otherwise it will become a superconductor, and superconductors are not possible at room temperature, right? So somehow the resistance still exists. But this conventional understanding, the classical understanding of resistance, is no longer explaining the resistance in these devices. So it is true that resistance is still there, but we do not know where it is coming from. And that's essentially one of the aims of this course. That in modern day devices, in the nanoelectronic systems, how does the electrical characteristics change? How does the resistance come into picture? Or uh, or how does the voltage drop in the device, because those things are not the same as they were in the previous in like 20 years back or 30 years back, right? So the key takeaway is, or the final takeaway point is that in let's say 20 years back, the transport of electrons was diffusive transport in transistors. Nowadays the transport is mostly ballistic transport. But the theory of the semiconductor physics, which explained the diffusive transport, it cannot explain the ballistic transport. So we need a new kind of understanding to understand the electrical properties of these modern day transistors. Okay, so let me ask you this. Let's say if we have an electronic device in which electrons, or in which this channel somehow becomes just 1 nanometer or few angstroms, then what would happen in that case? Let me give you an example. So there are some you might have heard about molecular electronics, in which the devices are made out of a single molecule between source and drain. So there is one source terminal, one drain, and in between we have a single organic molecule. The the distance between the source and the drain is only few angstroms, or 1 or 2 nanometers. In that case, what would be, or would the transport still be ballistic, or what would be the nature of electron transport? At atomic
I think it
dimensions, what would, yeah, please.
maybe it will stay ballistic.
Yeah, so it will be ballistic, but the, it goes even further. The transport or electrons travel as waves in a way. Yeah, so I'm trying to explain the difference between the pure quantum mechanical treatment of electrons. So in these devices, we need to consider the wave nature of electrons, the wave function explicitly. But in these devices, 10 to 20 nanometer, what we can do is we do not need to use this quantum, the wave nature explicitly, uh, and we can still in a way, capture the quantum mechanics in other parameters, and we can still assume that electron is still like a particle, but it is not undergoing any collision. It is going through a ballistic transport. So what I'm trying to convey is that even the ballistic transport is not a pure quantum mechanical treatment of electrons. Uh, it contains a lot of quantum mechanics, but it is still has classical element in it, because still we assume that electron is like a particle. Okay, and but this theory, the ballistic transport theory, is still applicable in our modern day devices, and it is a subject matter of nanoelectronics. Okay, so I wanted to clarify this at the outset, because after this course, you would be able to understand the quantum mechanical transport the pure wave nature of electrons as well. You would be ready to understand that, because although the most of, since we only have 20 hours of this course, so we cannot cover everything. I will, so that's why focus mostly on the ballistic transport in this course. Although if you are interested, we can, or any one of you is interested, you can send me an email and we can discuss about the quantum mechanical transport as well. Okay, so the subject matter finally is that in this course, we will mostly study about the idea of resistance. How does the idea of resistance come into picture in ballistic transport? And with the idea of resistance, the idea of voltage drop is also associated, and similarly, the idea of energy dissipation is also closely related to the idea of resistance. But I hope at the moment you would appreciate that the idea of resistance is not the same as it was in classical devices. So we need to revise this entirely. Okay. Uh, Let me quickly take you through the conventional understanding of resistance, which is the macroscopic resistance. And this comes from Drude's theory of conductivity, or Drude's model. So conventionally, the way we define resistance is that uh, the resistance is equal to rho times L by A, where rho is the resistivity, L is the length of the conductor, and A is the area of the cross-sectional area of the conductor, right? And where this quantity rho is equal to 1 by sigma. So this is resistivity and sigma is conductivity. And in Drude's model, the conductivity sigma is defined as n times E square tau by n. Right? I hope you might remember this from your previous courses, that generally in basic semiconductor physics course, this is the way we define uh, conductivity, then we define resistivity from here, and finally the resistance is defined in this way. Where n is the number of electrons in the system, E is the charge of electron. What is tau?
Is it the time between collisions, as I remember?
Exactly. So it is called as the mean free time. Right. So it is the average time between the collisions. So it is taken as the average of all the times that it takes between the two consecutive collisions by m. And based on this, we define, and this tau is also related to another parameter called lambda, which is the mean free path. Mean free path is the average distance between the two collisions, right? And this is of this order. This is around 0.1 micrometer. It may be larger as it may be 0.2, 0.3, depends on the material and the lattice structure. So this is how the resistance is defined in our uh, regular semiconductor physics courses. But and what we uh, generally take away is that resistance is proportional to the length of the conductor, or length of the channel. Okay, so this is our macroscopic resistance understanding of the macroscopic resistance. But now, at low dimensions, when the channel length is of this order, is so mean free path is 0.1 micrometer, which is around 100 nanometer or so. And if the channel length is even smaller than the mean free path, right? Channel length is 10 to 20 nanometer. In that case, transport is ballistic, no collision happens. What is tau? What does tau become in that case? Tau becomes undefinable actually, because there is no collision. We cannot define the time between two collisions, right? Or it becomes infinity because it does not happen. So in this case, the conductivity will become infinity from this Drude's model. If tau tends to infinity, in that case, the conductivity will also become infinity of the channel. But that does not happen. The conductivity is not infinite. It is not a superconductor. Okay, so this Drude's model does not work when the device is of the order of, or the channel length is of the order of mean free path, or smaller than the mean free path, which is the case right now, nowadays. So in ballistic transport, the Drude's model will not work. We cannot define the channel resistance in this way. Now the question arises, would the resistance still be proportional to the length? Because in the Drude's model, the resistance comes out to be proportional to the length of the channel. The question is, would the resistance still be proportional to length? And we do not know the answer at this point. That's the aim of this course, to understand these kind of things. So ultimately, in this course, what we take is we take a bottom-up approach. The Drude's model is a top-down approach. Top-down means that generally we consider a large device and we believe that electrons are scattering in this device, diffusive transport is happening. Then by taking the average between all the collisions, we find out tau, average time between the two collisions. And from tau, we define the conductivity, right? That is the top-down approach of the Drude's model, which works fine with macroscopic devices in the old transistors. But in the current technology of transistors, we cannot go by this. We need to we need to take the bottom-up approach. What it means is we need to understand the electrons conduction right from the fundamental physics of the electrons, right? And that's what we will take in this course, which means we would need to start from the basics. And what is the fundamental nature of electrons? The electron's fundamental nature is quantum mechanical. Electrons are quantum mechanical particles. So first, we need to briefly or very quickly understand the quantum mechanical properties of electrons in the solids. Then let me tell you this. One of the final results that we will get is we will come across this idea of quantum of conductance. So what we will obtain from this theory, which was initially given by Rolf Landauer in 1950s, 60s, for the resistance. Yes, anybody has a question? Please ask. Yeah, so I think somebody unmuted the mic. If you have a question, please ask. Otherwise, we can continue the discussion. Okay, so what I was saying is that this theory was given by Rolf Landauer in 1950s, 60s, but it was not directly applicable to the transistors. It was quite a complex theory at that time. Then it was refined by Supriyo Datta and Mark Lundstrom in 2000s, and that's how we use this Landauer transport model in our transistor nowadays. So what we realize is that the conductance is defined as G, which is 1 by resistance. This is the conductance. The conductance is a quantized parameter, which means the resistance is also quantized in small devices. In ballistic transport, the conductance and the resistance are quantized. And one quanta of the conductance is known as the quantum of conductance, and this is 2e square by h, where E is electron's charge, h is the Planck's constant. Or this is 1 by 12.9 kilo ohms. So this is one quanta of conductance, and this is one of the main results of the Landauer transport model. We will study the details of this a little bit later on, but I'm giving you a glimpse of what happens at nanoscale right in the beginning, so that we may appreciate the results at a later stage. And the resistance of a ballistic device can be written as, the resistance in ballistic regime can be written as RB plus RB times L by lambda, where RB is the ballistic resistance, which is defined from the quanta of conductance. And in this case, if the length of the channel is small, let's say this L is very, very small as compared to lambda. Lambda is the mean free path, this thing. So if L is very smaller than lambda, then this second parameter, second quantity, tends to 0. So the resistance that we are left with is only the ballistic resistance of the device. Okay, and this ballistic resistance is independent of the length. Okay, so these are some of the results that we will obtain once we go through the theory of or the Landauer transport model in electronic devices. Okay, and we will realize that things are fundamentally different from the classical devices. So this is the picture that we obtain at low dimensions. So at low dimensions, the resistance of the channel is RB times L by lambda. And in addition to channel, we have resistance at the interfaces as well. So the resistance of the source and channel contact is RB by 2. The resistance of drain and channel contact is again RB by 2. And the resistance of the channel is RB times L by lambda. Right? And if L is very, very smaller than lambda, in that case, this channel resistance tends to 0, but still we have the resistance at the interface. So the total resistance is still RB, which is a non-zero number. What it means is that in ballistic device in which L is very small, in that case, the channel resistance will be negligible, almost 0. The only resistance that will be there is the resistance at the source channel contact and channel drain contact. Okay, and that is why in ballistic devices, the resistance is called as the contact resistance. It comes because of the interface between the source and channel and drain. Okay. Yeah. Just a moment. Sorry, there was somebody. Okay. Okay, and is there any question till this point? Any doubt? Any comment? Anything you would like to add? Is the pace fine? Is the speed of lecture slow or fast, or what? Is this all right? Should I go with the same?
No, it's okay. It's fine.
It's fine. Okay. Anyone else? Okay, I'll assume that it's okay. Now, as we have seen that at low dimensions in ballistic transport, this picture of resistance has changed drastically, because now the resistance is not coming from the channel itself. The resistance is coming from the interface of the source and channel and drain. Because of this, the picture or the idea of voltage drop in the device will also change, because Now, or in a regular device, generally, how does the voltage drop? The voltage, so for example, if we apply a voltage V across, or V is equal to I times R, right? Where I is the current flowing through the device. So if resistance is uniform, which means if we have a conductor and there is a current flowing through the conductor, the resistance of the conductor is R, then the voltage drop will be like this, because V is I times R, and the voltage drop, let's say up to this point, will be I times resistance up to this point, which will be this. So voltage up to this drop up to this point will be current times resistance up to this point, which is this, because resistance is proportional to length. But in ballistic transport, there is a resistance at the contact and there is resistance in the channel, but the channel resistance is small because L is small. The channel resistance is RB times L by lambda. Because L is very small, so this almost is equal to 0. So now the most prominent resistance is only at the source channel contact and channel drain contact, right? So the voltage drop also happens prominently at the contacts. And in ballistic device, we would see that all the voltage that drops in the device, that happens only at the contacts. It does not drop in the channel. Okay, so that is a very distinct thing in these devices. If any question is there, please let me know. Otherwise, I'll move on. And similar to the voltage drop, the energy dissipation in the device. So as some of us might be aware that the heating of transistors, the heat dissipation in the device is a big issue, actually, always a big issue, because if too much heat is getting dissipated, then the device heats up, the temperature is increased, which changes the property of the electrical property of the transistor, which will change the current, the voltage, or the transistor becomes unreliable. Now, we also realize that in the ballistic devices, in the ballistic transistors, since most of the resistance is at the interface, which means that the energy dissipation, which is, or the power dissipation, which is I square R, it also happens at the interface. So the heat dissipation also takes place at the interface. And which means that now the contacts and this interface will be heated, not the channel, right? So this picture also changes. The picture of heat dissipation will also change significantly in the modern day transistors. So all these ideas we will come across in detail in, uh, uh, during the course of this in the later stages in the coming classes. We will discuss the mathematical details. We will derive equations of current in ballistic transistors and so on. I'm just giving you a glimpse of what we see. Okay, so now let's say we have this two-terminal device. Okay, so we have a device. So in this course, in first few classes, initially we will discuss the two-terminal device. Two-terminal means that there is a source, there is a drain, and in between there is a channel. We will not discuss about the gate in the beginning, because the gate is electrically insulated from the channel. So there is an oxide between the channel and the gate. So there is no flow of electrons from the gate to the channel. So that's why its effect can be considered later on. The most important part to understand is this two-terminal part of the MOSFET, this region, this two-terminal device. So that's why initially we just consider this kind of device. Now, in a nano device, okay, how do we visualize the conduction? Generally, if we apply a battery across this device, let's say the source is grounded, we put a battery here. How do we, or generally, what is the picture of channel that we have? Okay, let me be more precise. The thing is that now the channel is only few tens of nanometers, 10 or 20 nanometers. Because of the small length, uh, if the channel is long, let's say the channel is few micrometers, then in solids we have bands and band gaps, right? I hope you are aware of that. That in bulk solids we have the energy bands, in which the energy bands are essentially the energy range, allowed energy range of electrons, and band gaps, which is the disallowed energy range in the solids. But as we start shrinking the device, then we do not have bands and band gaps. We start having the discrete states of electrons. Okay, so this is the first thing that we always need to keep in mind, that in nano devices, the channel is not like a bulk semiconductor. It is a nanoscale semiconductor, which means instead of bands and band gaps, we will have discrete kind of states like this, right? So this is the way to understand channel. But let me give you an interesting fact, which you might already be aware of as well, that even in modern day devices, even in today's devices, the channel length is, let's say, 10 nanometer, but still the source and the drain are large. In this picture, you might think that the channel, the source, and the drain are of the same order, right? But it is not the case. Still, the source and the drain are, let's say, around 1 micrometer, or at least 0.1 micrometer length. And this is just 10 nanometer. Maybe in the next class, I'll bring you a real picture. So the actual picture of a transistor is that the channel is very small and the source and drain are quite large as compared to the channel. Okay, so what we can generally consider is that although in this this picture gives an impression that channel is long, source and drain are small, but this is drawn just for convenience. In an actual device, the source and drain are still quite large as compared to the channel. So the channel is nanoscale, but the source and drain are still slightly macroscopic, larger. So they still have bands and band gaps. Moreover, the source and drain are highly doped semiconductors. The channel is lightly doped. Source and drain are extremely highly doped as compared to the channel, which means that there are a lot of electrons available in source and drain as compared to the channel. So this is the picture of the channel. The channel have discrete states. Okay, and the available states in the channel, for that, we need to understand the density of states in the solids. Density of states means the number of allowed electronic states per unit energy per unit volume. Okay, so this concept we need to understand before understanding the ballistic transport. Okay, so please take a note of this, that in order to first understand the ballistic, the Landauer transport model, we first need to understand the density of states of the, especially the channel. The contacts, however, as I told, are still larger. Okay, which means what we can assume is that in contacts, although in channel the states are discrete, in contacts there is a continuum of states. The states will be continuously distributed. And we will see this a little bit later on while we discuss the quantum mechanical nature, why the states are continuous, which means that almost all the states in the contacts up to this level, which is called as the Fermi level, this EF is the Fermi level, EFS is the Fermi level of the source, EFD is the Fermi level of the drain. So all the states up to the Fermi level are filled in the source, as well as all the states up to Fermi level in the drain are filled. So this is the picture that we will be working. So please keep this in mind, that the channel is a lightly doped nanoscale semiconductor. The source and the drain are highly doped semiconductor, bulk semiconductor. As a consequence of that, in channel, we have discrete states, and in source and drain, we have a continuum of states. Moreover, what we can assume is, and there is an energy level called as the Fermi level. By the way, have you heard about Fermi level, or do you remember the idea of Fermi level from your previous courses? Can you please confirm that?
Yes, as I remember, Fermi level is the energy of electrons in the material, if I'm correct.
Yeah. So largely, the Fermi level is the energy up to which the states are filled in the system, in a solid. Okay, so this is defined as the highest energy up to which, or all the states below this level are filled at T equal to 0 Kelvin. So that's how we define the Fermi level. Okay, so the point that I'm trying to make here is that in order to understand the channel, we need to understand the density of states. But since source and drain are large, they are still bulk semiconductor. What we just need to understand is their Fermi levels. I will discuss this in more detail later on while I discuss the. So in this lecture, I'm giving you. So to this point, I'm giving you a broad perspective of the course itself. So the density of states and the Fermi distribution of electrons in the source and drain. These are two central ideas that we need to understand before going into the ballistic transport theory. Okay, I hope you appreciate this, that before understanding anything about the nanoscale devices, we need to understand these two concepts. One is the density of states. Second is the Fermi distribution of electrons in the source and drain. Now, you might ask, why don't we talk about the Fermi level of the channel? Right? You may have this question. So, let me answer this. So, generally, the Fermi level comes from the Fermi-Dirac distribution of electrons in the solids. Fermi-Dirac distribution is the statistical function. Fermi distribution is a quantum statistical, that comes from the quantum statistical mechanics. And generally, the Fermi level is precisely defined when the number of electrons in a system are large. So, because all of us know that we can define the statistics properly if the numbers are large for a bulk system. So what I am trying to say is that the Fermi distribution or Fermi function or Fermi level are defined properly for source and drain because these are the large systems. But they are not so precisely defined for the channel because channel is a very small system. The number of electrons in the channel is small. That's why a very rigorous definition of Fermi level cannot be given for the channel. So that's why in nanoscale devices, we avoid talking about the Fermi level of the channel. Although we can So I will discuss this idea when I talk more about the Fermi function later on. But uh, the thing that you can remember from here is that in channel we generally avoid defining the Fermi level because it is a statistical concept which is properly defined for large systems. And this is a nanoscale system. In this also we can define this, but that will not be a very rigorous definition. Okay, so just keep that in mind for the time being, and it will become clear later on. Okay, so this is the device, or this is a nanoscale device without bias. This is the picture of a nanoscale device without bias. Bias means there is no battery applied at the device, and uh, this is how it looks like, right? Now, what would happen if we apply a battery, a voltage bias to this device, which means the battery is connected to the contacts. This is how it would look like. Please take a moment and have a look at this. If we apply, generally the source is grounded and we apply a positive voltage on the drain. If we apply a voltage V on the drain, what does this voltage do? What does the battery do? A positive voltage on the drain means what will happen to the potential energy of the electrons? So the potential energy of electrons is Q times V. V is the voltage applied, U is the potential energy. Okay, and Q is the charge of electrons. But the charge of electrons is a negative number. So it is minus E times V, right? Where E is a positive unit of charge and minus is the negative charge of electrons. So on the drain terminal, the potential energy is decreased if we apply a positive voltage. If V is positive, U is negative. And what is the meaning of decrease in potential energy? It means that all the energy levels on the drain side will go down, including the Fermi level. Okay. So this is how the energy levels will change when a battery is connected to the MOSFET, to this two terminal or to the channel region of the MOSFET. So whenever we apply a battery on the drain terminal, this is how the energy levels will change in the device. Is this sort of clear or not?
Yes, it's familiar.
Okay, good. So now, how does the current flow in a device? Or what is the picture of conduction at low dimensions? So in a nanoscale system, in this device, the Fermi level of the source is up to this level, right? So what is the job of the Fermi level? The job of the Fermi level is to make sure that all the states below Fermi level, all these states below Fermi level are filled, right? So the source Fermi level, this is represented as mu and it can also be written as EFS. Similarly, the drain Fermi level, let's call it EFD. So what the source Fermi level do is that it will try to fill all the states below this energy level. Similarly, the drain Fermi level will also try to fill all the states below the drain Fermi level. Okay. Now the channel is connected to the source and the drain in this way, right? So it means that the source will try to fill all the states in the channel up to this level. So source will try to fill all these states because the source will try to bring the channel in equilibrium with the source Fermi. because all the states up to this level are filled in the contact. So if there is any state empty here in the channel, it will try to fill that state because electrons will go to that state to fill it. I hope this is clear, right? And similarly, the drain Fermi level will try to fill all the states up to this level. So it is also in touch with the channel, and so it will also try to fill all the states up to the drain Fermi level. In addition to that, on the drain side, the states which are above the drain Fermi level, the drain will try to empty them, to try to make them vacant. Because uh, in the drain side, there are no electrons here. Only electrons exist below the Fermi level. And if there is an electron in the channel here, and there is a vacancy here, electron will flow to this side. Okay. So in summary, what we can say is that ultimately what is happening in this device is that uh, the uh, the source is trying to fill all the states up to this level, drain up to this level, but these states, the states between the source and the drain Fermi level, the source is filling them, but the drain is trying to vacate them. Okay. So first of all, the states, these states which are below both the Fermi levels, so these states in the channel, they will be filled by both source and drain. So these states will always be full because the source contains a lot of electrons. Uh, the drain also contains lots of electrons, and the channel may or may not contain electrons in these states, but the states below the drain Fermi level, both contacts are trying to fill them. So they will always be full. But these states, the states which lie below, between the two Fermi levels, these particularly these two states, the source is trying to fill them, and drain is trying to vacate them. Are you? I hope you are getting this point, and that is how electrons are coming from the source to the channel, but they are being taken away by the drain. And then drain will supply these electrons to these additional electrons to the battery. If we have a battery connected here, and battery will again supply these electrons back to the source. That is how, so this is the flow of electrons in the device, and that is how the conduction works in any device actually. And so this is the direction of the electron flow, and the current will flow in the opposite direction, right? So the flow of current will be in this direction. Is this picture of conduction clear or not? So this is the conduction at, actually it is the picture of conduction at any in any device, but this becomes even more important for nanoscale devices. I think you might have some questions here. Please ask questions if there is any. Any questions, or is this completely clear? If that is the case, then we can continue.
I have one question. In the channel there is a gap. Is it a forgotten gap?
Yes, exactly. This. So yeah, in this, so you are talking about this gap, right?
Yes, yes.
Yes. So yeah, it is showing that there may be some energy levels at which no electrons are allowed. So it is the forbidden gap. Yeah.
Okay, thank you.
Okay. So okay, only that was. So let me clarify this a little bit more. this is the two terminal device that we are talking about, and this channel is amplified in a way. So in the channel region, the states may be discrete like this, right? So there may be discrete states, but it may happen that in the channel region itself, uh, at some points, we may have, let's say there are some states here, but there may be some gap as well. So it depends on the material of the channel. Depending on material to material, it may be the case, right? So I'm just drawing a very general picture here. Uh, in all cases, the conduction will happen in this way. In summary, what I'm trying to say is that the source is supplying electrons to the channel because source has a lot of electrons and there may be vacant states in the channel. And the drain whose Fermi level has been pulled down by the battery, it will extract electrons from the channel because its Fermi level is down. It has vacant states in front of the filled states, and that's how electrons will travel from source to drain. Then drain will again supply this electron to the battery, which is here in this way, and battery will again put this electron into the source. Battery takes the electron at the drain Fermi level and it supplies back at the source Fermi level. So this is the picture of conduction that we need to keep in mind. And this is true for a nanoscale, for a quantum mechanical, for a single molecule. In all cases, this picture holds true. Okay, so for example, if we have a quantum dot device, a quantum dot device means that there is a source contact, there is a drain contact, and there is a quantum dot sitting in between. A quantum dot is a very small channel, few nanometers or few angstroms. So the states of a quantum dot are like the states of an atom or a molecule. They are discrete states, right? So these are the states of the quantum. The states of the source is larger, so it will be represented by EFS. The drain is also larger, generally bulk as compared to the quantum dot. It will also be represented as via continuum of states. So there are continuum states here, and we have the source Fermi function and the drain Fermi function. Okay, and if we apply a battery across this, then the drain Fermi level will go down, let's say up to this point. Now the source Fermi level is here, the drain Fermi level is here. In between the two Fermi levels, we have two states in the quantum dot. So the source Fermi level will put electrons here and here, and these electrons will be taken by the drain. In these states, both source and drain will try to put electrons. But the current flow will happen through only these two states, right? So this picture holds true even for quantum dot devices, single molecule devices, single electron transistor, everything. We need to keep this picture in mind. And you might already be familiar with this. So I'll not spend further time on this. But if you have any questions, we can discuss that. Otherwise, I'll continue. Okay, so in a nutshell, uh, what we have discussed so far is that in summary, uh, the semiconductor technology is mostly concerned with the transistor at the moment. And in a transistor, in a MOSFET, this region is extremely important. This is the most important region of the transistor, which we draw here. So we will try to understand this region first. And this can be represented in terms of these two terminal devices, source, drain, and channel. And over last 40, 50 years now, this region is continuously shrinking, which is changing the fundamental physics of the transistor, because the earlier physics was driven by the diffusive transport. Now we need to understand the ballistic transport. Okay, and uh, the ballistic transport actually starts coming into picture when channel length is less than 10 to the power minus 7 nanometer, which is the mean free path of the channel. And because of this change, the idea of resistance changes, the idea of voltage drop changes, and the idea of energy dissipation changes. So most of the usual concepts about the devices change because of this. And in this course, when the university got in touch with me, I originally proposed this content for this course. So the first module of this course, as I proposed, was about the introduction, background, and fundamentals. So it was the focus that would be on, in my opinion, uh, on the necessity to understand and invoke quantum mechanics in nanoelectronics, and then introduction to quantum mechanics, which means Schrodinger equation, KP model, Brillouin zones, and these kind of concepts. The second module in my original proposal was about the Landauer's transport model for nano devices. And so this is the bottom-up approach of understanding the physics. And in this approach, in addition to explaining the nano devices, we can also explain the macro devices. So this theory, the Landauer transport theory, is not only for the nano devices, it actually is true for long devices as well. So that way it is a more general and more encompassing theory of the semiconductors. The third module that I proposed was about the MOSFET, especially the nano MOSFET. How does the nano MOSFET behave, and the electrostatics of the nano MOSFET and the transport of the nano MOSFET. In the fourth and the fifth module was about the advanced topics in nanoelectronics, which means the devices, the molecular quantum dot devices, and the first principle calculations. And the fifth one was some applications of these advanced concepts. But since this course is only, I think, is only for 20 hours, so I may not be able to cover everything here. So, but I will try to cover all the essential elements in all the modules. So I will try to cover the basics in quantum mechanics, the quantum mechanics that we need in this course, then the Landauer transport model, then the nano MOSFET, and some advanced topics. But if you are interested in some specific topic in nanoelectronics or quantum technology, uh, uh, you can get in touch with me over email, or you have any question, you can ask me separately. Okay. So from the entire discussion that we had about the nano devices, about the ballistic MOSFET, we can uh, we came to the conclusion that we first need to understand two basic concepts. First of all, the density of states in the channel, especially, and second is the Fermi function or Fermi distribution, Fermi level of the source and the drain. Because that from there we will build upon these two concepts and go to the Landauer transport model. And these two concepts, so that what is the density of states? The density of states is the number of energy states per unit volume per unit energy. So these are the allowed electronic states in a solid as a function of energy. Okay, and we need to use quantum mechanics to find out the density of states. Have you uh, done the density of states derivation in any of your previous courses? Do you remember that or not?
Yes,
Anyone?
we had courses about density of states and other quantum effects.
So do you still remember those concepts, or should I also go through this quickly?
I remember some of concepts, but not everything. So I think it would be helpful if you talk about
Go through.
them.
Okay, so I'll do this. I'll go through everything, but I may not be. I will not spend too much of a time on that, and but I'll go through everything. So I'm not assuming any of your background. Okay, so I think that will be better. So finally, what we need is, as I told, we need to understand DOS, density of states, and Fermi distribution. For that, we need to understand the quantum mechanical nature of electrons, which means we need to understand the basics of quantum mechanics. And as all of you are already familiar with quantum mechanics, so I will not, again, I will go through everything in quantum mechanics, but I'll not be too rigorous about it. So the first thing, or one of the fundamental postulates of quantum mechanics is that for each quantum system, in order to describe the system, in order to describe the properties of the system, we need to define the wave function of the system. So if we need to understand or if we need to uh, characterize electron in quantum mechanics, we need to define a wave function. And a wave function, as the name suggests, is a mathematical function belonging to the Hilbert space, a complex a valued uh, inner product space, vector space. So this is a purely mathematical quantity which contains all the information about a quantum system, right? I hope all of you know this. And but it does not, so the wave function directly does not have any physical interpretation, or does not correspond to a physical quantity in the real world. It is a mathematical concept, and it belongs, or the way we say it, that it is a vector in the Hilbert space of the system. Okay. Now, the physical meaning to the wave function was actually given by the Born interpretation. Max Born proposed that the way we should understand function is by the probability density interpretation, which was actually accepted in the Copenhagen interpretation of the quantum mechanics as well. What it says is that if we define psi star psi, where psi star is the complex conjugate of the wave function and psi is the wave function itself, which is essentially the mod psi square. Now, this quantity is the probability density of finding the particle in the space, time, essentially. And what do we mean by probability density? So the probability density means, so let's say that we only have a wave function for x. Let's say we have a particle in one dimension only. So psi square x is the probability density of finding the particle in the x-axis, on the real line in the x-axis, which means if we want to find out the particle between x1 and x2, the total probability of finding the particle between x1 and x2 is, between x1 and x2 is the integration of the probability density from x1 to x2. So probability density when integrated over space gives us the probability of finding the particle in that region of the space. Okay, that is the Born's interpretation of the wave function. And that's what we generally take in our solid state physics as well. There are alternative interpretations as well. We'll not go into that, right? So in quantum mechanics, we have a mathematical function, wave function, and the way we interpret the wave function is via probability density, right? Then, in order to find out the physical quantities of the system, let's say we have the wave function of an electron, but we want to find out the momentum of the electron or energy of the electron, we need to define another mathematical operators. We need to define what is known as measurables. These are Hermitian operators, and I hope, given your background, you will already be aware of terms like Hilbert space, the Hermitian operator, and like that. So these are again mathematical quantities. When we operate them on the wave function, they give us the values corresponding to the physical parameter that they are describing. So for example, the energy operator, the total energy operator is I, imaginary number h bar, divided by del T. This is the energy operator. Similarly, the momentum operator is minus I h bar del by del x is the momentum operator. So what it means is that if we apply these operators on the wave function, they will give us some value. Or if the wave function is the eigenfunction of these operators, then we will get some value m times the wave function again. Otherwise, it will be the sum of the eigenfunctions of these operators. Mi phi I x, where phi I is the eigenfunction of the operator. So via operators, we extract the physical quantities, the physical properties of the quantum system. Okay, I'm just giving a very quick review of the quantum mechanics, the postulates, the basics of quantum mechanics. And the related quantity is the expectation value of a certain operator. So the expectation value is essentially the average value of that operator, which means that if we are given a wave function, what is the average momentum of an electron whose wave function that is, right? That is given by the expectation value, and the way we calculate the expectation value is we integrate that operator, let's say the momentum operator, we put it between psi and psi star and integrate over the space in which we want to find out the average values. Here, I would like to mention that if we have a wave function and we make a measurement on that wave function, then the wave function would collapse to certain state, to a eigenstate of the measurement operator. And the outcome will be one of the eigenvalues of the measurement operator. But if we do a large number of measurements, then we take the average of all the outcomes, that is given as the expectation value of that operator, and that is how it is calculated. Okay. When we deal with a system of multiple electrons, let's say we have a lot of electrons in the system. In those cases, most of the times we are mostly concerned about the expectation value. So that's why it is an important quantity which needs to be kept in mind. Right. So this is about making sense of the wave function that is done via the operators. Now, after this, we also have what is called as the evolution of the system. How does the system change, or how do we find out the state of a system when in a certain situation? That is given by the Schrodinger equation. Okay, and in a very simple form, this is the time-independent form of the Schrodinger equation. In the most abstract form, the Schrodinger equation is h hat psi is E psi, where h hat is the Hamiltonian of the system. Hamiltonian is the total energy operator of the system. Psi is the wave function. E is the energy eigenvalue. Psi is the wave function. But when the total energy of a system is constant, which means that the energy of a system is not changing as a function of time, in that case, we can separate the time dependent part and the time independent part of the wave function from each other. And that way we can define what is called as the time independent Schrodinger equation. Time independent Schrodinger in most of in our let's say in our MOSFET or in our solid state systems, generally this assumption is valid because generally the energy is not changing dynamically, so we can uh, separate, or we can approximate this Schrodinger equation by the time independent Schrodinger equation, and later on if we want to find out the time evolution as well, that can also be found out. Okay, and so these are some of the basic things that we have a wave function. There is a probabilistic interpretation of the wave function. In order to find out the physical quantities, we define operators called measurables. Then an evolution of the system is given by the Schrodinger equation. In addition to this, according to Max Born himself, when he was proposing the physical interpretation of the wave function, there are some other conditions that the wave function needs to satisfy in order to be a valid wave function for a physical system, right? And these conditions are that the wave function should be single valued. And it is easy to understand because single valued means that it should not take multiple values at the same point. And we can understand that because now same particle, same electron cannot have multiple probabilities at the same point. It is just unphysical. This is not a physically reasonable thing. Okay. Second property is that the wave function should be square integrable, which means that this integral psi star dx, we are talking about just one variable, x variable, should be well defined for all x1 and x2, which means it will be less than infinity. Moreover, from the probabilistic interpretation, what we uh, conclude is that this integration from minus infinity to plus infinity psi square dx should be 1, exactly 1. Because psi square is the probability density of the particle being found in a region of space. The total probability can only be 1. It cannot be more than 1 or less than 1 over the entire space of existence. Okay. So the wave function should be single valued, square integrable, and normalizable. Okay. Second is that the wave function, or the third property is that the wave function should be continuous. Can anybody comment why the wave function should be continuous? In why the in quantum mechanics, why the wave function should be continuous? Not only the wave function, the first order derivative of the wave function should also be continuous. So these are two other properties that a wave function should satisfy. I hope you are aware of these properties, but can you please recall why that is the case?
I don't remember this. Why?
Okay, so the reason is that if a wave function is not continuous, in that case, it's so I'm giving you first of all a mathematical reason. The mathematical reason is that if the wave function is not continuous, it means that its derivatives cannot be defined. It does not have a finite derivative, which means that we cannot define the energy, the momentum of the system. So any physical particle, let's say any electron, will always have a valid momentum varied energy. Any physical system will have these things. So for that, we need to have the continuity of the wave function. That is the mathematical reason. The physical intuitive reason is that a discontinuity in a wave function means that the discontinuity will also be there in the probability density, which means that somehow magically the particle is existing in a certain region of space, but it suddenly disappears from one region and appears at the some other place, which is also not physically justifiable for a real particle. But generally, we have the mathematical justification that its physical quantities should be well defined. Similarly, the first order derivatives should also be continuous. And the reason for that is also quite similar because the energy operator can also be written as in terms of the space. It is written as the second derivative of the x minus h bar square by 2n del 2 by del x2 plus the potential energy. So this is u, which is the potential energy operator of the system. So if the first order derivative is not continuous, then we cannot define the kinetic energy of the system. So this is the kinetic energy operator of the system. Okay, so for any physical quantum mechanical system, the wave function should be single valued. It should be square integrable. Moreover, this integral value should be 1. The wave function should be continuous. Its first order derivative should also be continuous to properly define all the physical quantities associated with the system. Although this continuity of the first order derivative, in some cases, it may not hold true. For example, if we have a sudden potential change and a delta potential in the space, then this may not be true. Okay. So we will see that or you might also remember that while solving Schrodinger equation for a delta function, this condition does not hold true. Okay. But roughly for all physical systems, when the potential energy is finitely defined and is changing smoothly, then these 4 properties should be valid: single value, square integrability, continuity of wave function, and first order derivative. Okay, so this is the all the postulates or the basics of quantum mechanics that we need. Just this. With this, we will be, and the first job that we have in our hand is to understand the nature of the electrons. Okay, and that's what we will do with these basic tools in our hands. These quantum mechanical description, we will be able to understand the nature of electrons, especially in simple scenarios. So the first scenario that we take is that of a free electron. Ultimately, we want to understand electrons in solids, but we will not directly jump to that. That may be slightly complex to understand. First, we will briefly try to understand how does a free electron behaves. Okay, and then we will gradually go to the electrons in solid. But what do we mean by free electron? What do you understand by a free electron? Or what is a free electron?
It's an electron that does not have bonds with atoms.
Yes, exactly. So a free electron is the electron which is not bonded to anything. Or to be more general, an electron that is alone in the universe. That is not interacting with anybody else in the universe, which is free from all the interactions. What does it mean? It means that the potential energy of the electron is 0 because potential energy arises or potential energy is constant, and we can take that as a 0 value reference value because the potential energy changes due to interactions. So if the electron is not bonded to atoms to anything else, it is not under the influence of any external electric field or magnetic field, we can say that it is completely free, it is alone in the universe. Now for this electron, what is the Schrodinger equation? Because we want to know the state of this electron, we want to know the wave function of this electron. The Schrodinger equation again is, we will write down the time independent formalism. It is minus h bar square by 2m del 2 psi plus q psi is equal to E times psi, where this is the kinetic energy operator, this is the potential energy operator, and this is the total energy of the electron. So if we have a free electron with total energy E, is then this then we can say that the potential energy is zero since it is not having any interaction. So the Schrodinger equation changes to this. And if we only consider, let's say, one variable, x variable, this is how the Schrodinger equation changes. And can you quickly solve this equation uh, del 2 psi by del x2 plus 2me by h bar square psi is equal to 0. So this is the Schrodinger equation for a free electron. This is a simple second order differential equation of the wave function, right? The simple mathematical equation which describes the state of the electron. Although the time is over, I'll take, can I take a couple of more minutes to just finish this, and then we can close the class, right? Can I take just
Yes,
2 more
I think.
minutes? Yeah. So this is the Schrodinger equation for the free electron. Can you recall, or can you solve this equation, or what will be the solution? What will be the value of the wave function? You might remember it from your previous courses, uh, uh, or it's a simple mathematical second order differential equation. You can also guess the solutions. So the solutions of this equation, in case you do not recall them, are like plane wave solutions, sinusoidal plane wave solutions. So this is the similar equation that we obtain in our classical wave theory, wave propagation theory, in which we have a second order uh, equation. It also appears in electromagnetism. The solutions are, in 1D case, the solutions are quite simple. So this equation can be rewritten as del 2 psi by del x2 plus k square psi is equal to 0, where k is this quantity. K is square root of 2me by h bar square. Now the solutions of this equation can be written as, one way to write the solution is psi x is equal to uh, a e to the power I k x plus b e to the power minus I k x. And if you put this value of psi x in this equation, you would see that this is a valid solution of this differential equation. Right? I hope you agree with this. And another way of writing down the solution is a sine kx plus b cos kx. So these are simple plane wave, sinusoidal plane wave solution of the Schrodinger equation, right? So a free electron, in a nutshell, has sinusoidal plane wave solutions as we have just derived. And so the solution looks like psi x is a sine kx plus b cos kx. Secondly, this integral psi x square in the entire region of space should be 1. So that is the only condition, because for finite values of a and b, this function is a single valued function, and according to the Bond's interpretation, this should be obeyed. Now this parameter k is an interesting parameter, and k was defined as square root of 2ne by h bar square, or e can be written as h bar square k square divided by 2n. Right? So what it means is that a free electron does not have any restriction on the energy values. That is the key takeaway here. A wave function would exist, psi x would exist, whatever be the value of E. It is independent of the E values. So, which means all energies of a free electron are permitted. And in solid state physics, in our electronics, we are generally concerned about the EK diagrams, which is the relation between energy and the wave vector k. In this case, what would be the EK plot? It would be just a simple parabolic relation between E and K, right? If the K values are positive, E is positive. If K are negative, still E will be positive, and the variation will be this. So for a free electron, the electron that is free from all the interactions, the wave function is the plane wave solution. From this wave function, we can calculate all the momentum and rest of the properties of the system. And the EK relation between energy and wave vector is a parabolic one. And there is no restrictions on the energy values. Okay, but in real life, no electron or no particle or nobody is free from interactions. Everything is interacting with everything or rest of the universe. So this is the benchmark, or this is just for reference, that if electron does not interact with anything, this is how it will look like. But no electron is free. Now the second case that we will consider is the case of electron in a potential well, when electron is confined in a potential well. I will not discuss that. Maybe I'll begin that discussion in the next class. Okay, so this is the review of what we just discussed. These are some of the basic postulates of quantum mechanics, and this is how the free electron behaves. Now we will gradually go to the electrons in solid, and then we will go to the density of states. From there, we will go to the Landauer transport model. Okay. So I will stop here. If there are any questions, please ask. We can discuss. Or any feedback, any comment about or should about the way we conduct class? Should we go? Should we take 1 hour and take a break in between, or is this fine? The continuous 2 hour is fine.
I think it's fine.
Yeah, I do think so. Any other questions or anything else?
No, it's clear.
Okay, thanks. So thank you all of you, and thank you for attending. Thank you for the attention. Let's meet on Wednesday. And if you get any questions, you can post on NS Teams, or you can also send me an email. Okay. So bye-bye, all of you. See you on Wednesday.
Thank you. Okay, goodbye.